Hello. In this video, we are going to look at the Latimer diagram for sulfur in basic solution in some detail. Balancing reduction half reactions in basic solution is very much like the similar process in acidic solution, with one further complication. One technique, which I often call a trick is just a shorthand for a legitimate mathematical technique that is convenient to use. This trick that we're going to use is the fact that if we react hydrogen ion with hydroxide ion, it forms water. Now, we write it with this double arrow to show that there's an equilibrium between the concentrations of H plus and hydroxide on one hand, and on the concentration of water on the other hand. However, we know that at 25 degrees centigrade, 298.15 Kelvin, that the equilibrium constant for this reaction is overwhelmingly much larger than 1. The equilibrium constant for the reverse reaction, for the ordered dissociation of water, we know is 10 to the minus 14. Therefore, the equilibrium constant for this particular reaction is 10 to the positive 14, which is a number significantly larger than 1. So therefore, we will be justified in the technique that we're going to use throughout this particular video in adding H plus and OH minus and writing them down as if this particular combination of ions invariably gives us the molecule of water, because in reality, overwhelmingly, that is true. In the first reaction in our Latimer diagram, we have sulfate ion being reduced to sulfite ion. So we have sulfate ion, SO4 2-, being reduced to sulfite ion, which is SO3 2-. We note that the oxidation number for sulfur in sulfate is +6. And I have a video where I go into the oxidation numbers of sulfur in various molecules and ions in great detail, which you can find if you look in the upper right-hand corner. In sulfite, we see that the oxidation number for sulfur is +4. So to reduce sulfur from +6 to +4 is going to require 2 electrons. So to balance the oxidation numbers, we need to add 2 electrons to the left-hand side. We also notice that the number of oxygen atoms on each side does not balance. So we have 4 oxygens here and 3 oxygens over here. So we're going to continue with our standard technique of balancing by adding 1 molecule of water on the right-hand side, because that will balance the number of oxygen atoms. Now, that works okay with the oxygens, but now we realize that we have 2 extra hydrogens on the right-hand side that we don't have on the left. So therefore, we have to add 2 H pluses to the left-hand side. Now, if this particular reaction were taking place in acid, we would have satisfactorily completed our half reaction balancing here. But recall that this is a reaction that takes place in base. So remember, in base, the concentration of hydroxide ion is much greater than the concentration of H plus. So we have to account for that fact. And the way that we account for that is to essentially neutralize all the H plus on the left-hand side. And the way that we do that is by adding 2 hydroxide ions to each side. So we add 2 hydroxide ions to the left-hand side, and similarly we have to add 2 hydroxide ions to the right-hand side. Now that we've done that, we add our entries, and we see that if we do that, we get our sulfate on the left-hand side, which is not a surprise. And nothing happens to our 2 electrons. But now we've added proton plus hydroxide ion. So that gives us 2 molecules of water. That's the equilibrium that we're making use of that I mentioned earlier. Now for the right-hand side, everything is exactly as we'd expect. We simply add together the sulfite ion plus the molecule of water, and then the 2 hydroxide ions. And now that we've done that, we are almost done. And by say almost done is we realize that we have 2 molecules of water on the left-hand side and 1 molecule of water on the right-hand side. So now we can simply subtract 1 molecule of water from each side, and I will, to save myself some writing, I will simply erase on the right-hand side, and I'll reduce the coefficient here to 1. So now we have the balanced oxidation-reduction reaction in base. And it's good to double check to make sure that we have the correct number of atoms on each side, because we have 1 sulfur, we have 5 oxygens, so here we have 3, 4, 5. We have 2 hydrogens here, and we have 2 hydrogens there. Therefore, this is the balanced half reaction for the reduction of sulfate to sulfite in basic solution. In our second reaction, we are going to look at the reduction of sulfite ion to tetrathionate ion. We notice in this particular reaction that we have sulfite ion, and that the oxidation number of sulfite is +4 for the sulfur atom. Whereas in tetrathionate, we have the odd situation that the average oxidation number of each sulfur atom is 2.5. This is a complicated problem for other reasons as well. We notice that we have just 1 sulfur atom on the left-hand side, and we have 4 on the right-hand side. So we need to account for that by changing the coefficient. So to figure out how many electrons we need to transfer, it's easier to think of the sulfur atoms in aggregate rather than individually. So if each of the sulfur atoms here has a oxidation number of +4, and there are 4 of them, altogether they have an oxidation number in aggregate of +16. On the other hand, on the right-hand side, we have 4 atoms that each have an average oxidation number of +2.5. So therefore, in aggregate, it's +10. So we go from +16 to +10, and that tells us that we have a transfer of 6 electrons. So if we add 6 electrons to the left-hand side, we will properly account for the change in oxidation numbers. Now that we have done that, we need to balance the number of oxygen atoms on each side. That's our standard procedure. So here we notice that we have 12 oxygen atoms, whereas on the right-hand side, here we only have 6. So we need to account for 6 more, and we do that by adding 6 molecules of liquid water. And that looks good. Now the oxygens and sulfurs are balanced. We need to account for the hydrogens. And we notice that we have 12 hydrogens, so we add the 12 hydrogens to the left-hand side. And this is exactly what we would have done if we were balancing the reaction in acidic solution. But recall that we're doing it in basic solution, where the concentration of H plus is going to be very much smaller than the concentration of hydroxide. So we account for this by adding the appropriate number of hydroxide ions to each side. And the appropriate number is always going to be exactly as many hydroxides as we have protons. So we're going to add 12 hydroxide ions to each side. And I'll color code my oxygen atom there. So we add the same to each side, so that's legitimate mathematically. So now we can add together. So we have our 4 sulfites on each side. My 3 look a little better there. Sorry about that. We have our 6 electrons. That does not change. And then we're going to add the protons plus the hydroxide to give us 12 molecules of liquid water. Put our arrow here. And then, the proper charges in for each ion. That's very important. Plus we have our 6 H2Os and our 12 hydroxides. And we'll put our oxygens in there. And that is all properly balanced. Anything else we need to do? Well, we have one last task. And that is we realize that we have 12 waters on the left-hand side and 6 on the right-hand side. And as a general rule, when we're balancing reactions, we do not want to have the same species in the same form as both a reactant and a product. In effect, it's acting as a spectator. So to correct for that, we need to subtract 6 water molecules from each side. So if I subtract 6 water molecules from the right-hand side, this term disappears entirely. And then from the left-hand side, it converts the 12 into a 6. And we can double check that we have the correct number of oxygen atoms. This is a good double check. So we see that we have 12 plus 6 is 18, and then we have 6 plus 12 is 18. So since the number of each atoms is correct, we've properly accounted for the change in the oxidation numbers of sulfur. This is now the correct balanced half reaction for the reduction of sulfite to tetrathionate ion in basic solution. Next, we are going to examine the reduction of tetrathionate ion to thiosulfate ion in basic solution. We notice that in tetrathionate ion we have 4 sulfurs, whereas in thiosulfate we have only 2. Therefore, we can balance the number of sulfur atoms by putting a coefficient of 2 in front. Notice at the same time this also fortuitously balances the number of oxygen atoms as well. So now let's look at the oxidation numbers. Recall that in tetrathionate the average oxidation number is plus 2.5. In thiosulfate the average oxidation number is plus 2. So from the point of view of in aggregate, the sulfur atoms on the left-hand side have a total oxidation number of plus 10. On the right-hand side, each is 2, but notice that we have 4 of these sulfurs. So that gives us a total oxidation number of plus 8 for all the sulfurs in all the molecules on the right-hand side. So we're going from plus 10 to plus 8. So that's going to require the transfer of 2 electrons. Now notice, since we've already balanced the number of oxygen atoms on each side, we do not need to introduce molecules of water, protons, or hydroxide ions at all. So this can be a somewhat tricky problem in the sense that it's easier than the average problem, so therefore we might want to introduce complications into it that we simply do not need to do it. And we can double check that we've satisfactorily corrected the problem by noticing that on the right-hand side, the total charge is we have 2 molecules, 2 ions, that each have a charge of minus 2, so that gives us a total charge on the right-hand side of minus 4. On the left-hand side, we have a total charge of minus 4 as well. So the charge is balanced, the number and identity of each type of atom is correct. So therefore, this is the balanced half reaction for the reduction of tetracyanide ion to thiosulfate in basic solution. Next, we are going to look at the reduction of thiosulfate ion to elemental sulfur. We notice that in thiosulfate we have 2 sulfur atoms, whereas in our elemental sulfur over here we have just 1. So the first thing we want to do is to balance the number of sulfur atoms on each side. Next, we recall that the oxidation number of sulfur in thiosulfate is an average of +2, whereas the oxidation number of sulfur in elemental sulfur is going to be 0. So for just one sulfur atom to reduce from +2 to 0 would require 2 electrons, but we have 2 sulfur atoms, so that's going to require 4 electrons. Next, we notice that we have 3 oxygen atoms on the left-hand side, but 0 on the right-hand side. So we'll correct that in the standard procedure by adding 3 molecules of water to the right-hand side. And now we have the correct number of oxygen and sulfur atoms on each side. But we don't have the correct number of hydrogens. So we have 6 hydrogens on the right, so we're going to need 6 hydrogens on the left-hand side. This would be perfectly balanced if we were doing it in acidic solution, but recall that we're doing it in basic solution, so we have to add 6 hydroxide ions to each side. Once we've done that, we're going to again make use of the fact that when we react protons and hydroxide ions, the equilibrium is overwhelmingly on the side of them combining to form liquid water. So we're going to write the left-hand side as S2 plus our 4 electrons, which don't change. And now we have 6 molecules of liquid water. So that is our left-hand side. And on the right-hand side, we still have our 2 atoms of elemental sulfur. And we have 3 molecules of H2O and 6 hydroxide ions. And we're almost finished. Our final step is to realize that we have liquid water as both a reactant and a product, and if it's doing that, it's acting as a spectator. So we need to subtract 3 molecules of liquid water from each side, so simply erase it on this side, and on the left-hand side, when we subtract it out, it gives us a coefficient of 3 for the H2O. Last but not least, we want to double check to make sure that the charge is balanced, for example. So on the right-hand side, we have a -6 charge. On the left-hand side, we have a -6 charge. We have 3 plus 3, 6 oxygen atoms. We have 6 oxygen atoms on the right-hand side. On the left-hand side, we have 6 hydrogens. On the right-hand side, we have 6 hydrogens. Therefore, we've correctly worked out and balanced the reduction half reaction for thiosulfate to elemental sulfur in basic solution. We now want to look at the reduction of sulfite ion directly to elemental sulfur in one step. In sulfite, the oxidation number of sulfur is +4, whereas the oxidation number of sulfur in elemental sulfur is 0. Since we're going from +4 to 0, we must have gained 4 electrons. So adding 4 electrons to the left-hand side, writing it as a standard reduction, will properly account for the oxidation numbers of sulfur on the left-hand side going to the oxidation number on the right-hand side. All well and good. Now we have 3 oxygen atoms that are on the left-hand side, but none on the right. So we know how to handle that. We're going to add 3 molecules of liquid water to the right-hand side, and that will properly balance the number of oxygen atoms. Adds another problem, though, that now we have too many hydrogen atoms on the right-hand side. So we can fix that by putting 6 protons, 6 H+ ions, on the left-hand side. As we've seen before, this is the correct half reaction if we were doing the reaction in acid. But we're not. We're doing it in base. So in base, we need to neutralize all of the H+ by adding the appropriate number of hydroxide ions. That's going to be 6 OH- to each side here. And now that we've done that, we can add each of the sides. So we have our sulfur atoms. We can add our oxygen in here. So we have SO3. We make use of the fact that if we combine a proton with hydroxide, we're going to get 6 molecules of liquid water, because that's what the equilibrium overwhelmingly favors. Then on the right-hand side, we have 3 molecules of water and 6 hydroxide ions. And now the last step is we realize that we have water as both a reactant and a product. So therefore we can correct this by subtracting 3 molecules of water from each side. If we remove these 3 molecules of water and remove 3 here, we just change the coefficient. And now we have the appropriate half reaction that takes place in basic solution. One way to recognize that you have a reaction taking place in basic solution is the presence of hydroxide ion in the equilibrium somewhere. Just as if you see H+, that's a sign that the reaction is taking place in acidic solution. As one last check, let's make sure that we have the proper charges. -2, -4 gives us -6, and we have -6 on the right-hand side. Similarly, we have the correct number of oxygen atoms, 6 and 6, and we have 6 hydrogens here and 6 hydrogens there. Therefore, we've properly balanced this reaction in basic solution. For our final reaction, we want to look at the reduction of elemental sulfur to sulfide ion in basic solution. The oxidation number of sulfur in elemental sulfur is 0, as it is for any element. And the oxidation number of sulfur in sulfide, S2-, is going to be -2. The oxidation number of any monoatomic ion is simply the charge on the ion. Since it's going from 0 to -2, it must have picked up 2 electrons. So we add our 2 electrons to the left-hand side, and we notice that the number of sulfur atoms balances. The charges are the same on each side. Notice now, again, we did not have to add any molecules of water, no hydroxide, no protons, because it wasn't necessary. So this is a nice reaction, and it's incredibly simple, but we've balanced it correctly. Thank you very much for your kind attention, and as always, have a good one.